Now, we will study the motion of a simple apparatus called mathematical pendulum operating under the influence of gravity. Mathematical pendulum is an idealized model of simple pendulums. A simple pendulum consists of a small bob suspended by a string or a rod from a rigid support or the ceiling, as seen in the photo. We will approximate the simple pendulum with its mathematical model, where a point-like bob or point mass m is suspended from the fixed point P with a string of the length L. The string has a negligible mass and cannot be stretched, and we will also neglect the drag force acting on the moving bob due to the air resistance. Then there is only one unconstrained force acting on the point mass, which is the gravitational force given by the mass m times the gravitational acceleration g. The constrained force F' exerted on the point mass by the string or the rod is the opposite force to the weight of the point-like bob. If the pendulum is at rest, the string or rod is in a vertical position and the bob hangs at the end of the suspension in equilibrium. When the bob is displaced from its equilibrium position and then released, the net force given by the vector sum of the gravitational force g and the constrained force F' accelerates the body in the direction of the equilibrium position. As a result, the bob will swing back and forth around its equilibrium position along an arc between its turning points. In other words, the point mass in the idealized model starts a periodic motion or oscillation in a vertical plane. Therefore, the motion of the pendulum is planar motion, and the pendulum is also called planar pendulum, where the whole suspension string or rod moves along the vertical plane determined by the initial velocity of the bob. However, we can talk about other types of pendulum in terms of the initial velocity of the bob. We perform experiments with a conical pendulum. If we push the bob displaced from its equilibrium position such that its initial velocity is perpendicular to the plane determined by the equilibrium position and the displacement of the bob. As a result, the trajectory of the bob will be a circle in the horizontal plane determined by its initial position, and the string or rod moves along the conical surface with the apex determined by the suspension point P and the base determined by the circular path of the bob. In the general case, the initial velocity of the bob is not perpendicular to the plane determined by the equilibrium position and the initial displacement of the bob, and its trajectory can be a complicated curve on the spherical surface determined by the length of the suspension string or rod. A pendulum performing such a motion is known as spherical pendulum. Here we only study the motion of the planar pendulum depicted in the figure. The instantaneous position of the point mass m representing the bob can be described by the angle phi between the vertical line PO and the suspension string of the point mass. The point P is the point of the suspension and the point O denotes the equilibrium position of the pendulum. The length of the suspension string is denoted by L. The instantaneous displacement of the mathematical pendulum is given by the angle phi, which is measured counterclockwise. Then the arc length S covered by the moving bob from the point O is positive to the right of the equilibrium position and negative to the left of the point O, and it can be written as the length L times the angle phi where the angle is measured in radians. The only unconstrained force acting on the moving point mass is the gravitational force given by the mass m times the gravitational acceleration g. We can decompose the weight g to the components tangential and perpendicular to the path of the motion. The magnitude of the tangential component can be written as the mass m times the magnitude of the gravitational acceleration g times sine phi, whereas the magnitude of the normal component is given by m times g times cosine phi. The constrained force F' is exerted on the point mass by the suspension string, where F' and the normal component of the weight g have opposite directions. As already mentioned, we neglect the frictional force acting on the moving mass point. Then the net force F acting on the point mass is the vector sum of the weight g and the force F'. Now we can apply the fundamental equation of dynamics stating that the net force F acting on the point mass m is equal to the mass m times the acceleration a of the point mass. The equations of motion of the bob traveling along the arc are the components of the fundamental equation of dynamics. For the tangential direction we can write that the mass m times the magnitude of the tangential component of the acceleration a is equal to the magnitude of the tangential component of the net force F, which is equal to minus the magnitude of the tangential component of the weight g. The minus sign indicates that the tangential component of the weight g points in the opposite direction to the tangent to the path of the bob moving from its equilibrium position O to its turning point in the right-hand side. Similarly, for the normal direction we can write that the mass m times the magnitude of the centripetal acceleration is equal to the magnitude of the normal component of the net force F, which is equal to minus the magnitude of the normal component of the weight g, plus the magnitude of the force F'. The minus sign in the front of Gn indicates that the normal component of the weight g points in the opposite direction to the normal to the trajectory of the bob. In the discussion on the motion of a point-like body along an arbitrary curve, we determined the tangential and normal components of its acceleration. We saw that the magnitude of its tangential component is given by the second-order derivative of the arc length s covered by the body with respect to the time t, whereas the magnitude of its centripetal acceleration can be written as the square of the speed v of the body divided by the curvature radius measured for the path of the body at its instantaneous position, which is equal to the length L in the case of the bob moving along an arc with the radius L. By substituting the components of the acceleration of the point mass and the force acting on it, we obtain the equations of motion of the pendulum, which are the following. In the tangential direction, the mass m times the second-order derivative of the arc length s with respect to the time t is equal to minus the mass m, times the magnitude of the gravitational acceleration g, times sine phi. In the normal direction, the mass m times the square of the speed v divided by the length L is equal to the magnitude of the force F prime, minus m times g times cosine phi. Since the arc length s covered by the moving bob is equal to the length L times the angle phi, the tangential component states that the second-order derivative of the angle phi is equal to minus the ratio of g to L times sine phi. We can use the normal component to compute the magnitude of the force F prime acting on the bob if we already determined its speed v at the instantaneous position for a given angle phi. We only need to solve the differential equation describing the tangential component of the fundamental equation of dynamics. The differential equation can be written in the form stating that the second-order derivative of the angle phi measuring the deviation of the pendulum from its equilibrium position with respect to the time t, plus omega squared times sine phi is equal to 0. Here the constant omega is defined by the square root of the magnitude of the gravitational acceleration g divided by the length L of the suspension string of the pendulum. This is the final form of the equation of motion of the mathematical pendulum, and we see that it depends only on the parameter omega whereas it is independent of the mass m of the bob. If we assume that the pendulum swings through a small angle, that is the maximum of the angle phi is small, then we can approximate the sine of the angle with phi itself in the first order. As a result, the second term in the left-hand side of the equation of motion reduces to omega squared times phi, and we obtain the equation of motion for a harmonic oscillator. The solution to the oscillator equation states that the instantaneous displacement of the mathematical pendulum measured by the angle phi is equal to the initial angle phi 0 at the turning point, times the sine of the sum of omega times the time t and an initial phase shift angle alpha. In other words, the bob performs a simple harmonic motion for small swings, where the parameter omega is the angular frequency of the periodic motion. Then the period t of the oscillation is given by 2 pi times the square root of the length L of the suspension string divided by the magnitude of the gravitational acceleration g. Let us solve the equation of motion for the mathematical pendulum in the general case, and consider the original equation stating that the second-order derivative of the angle phi with respect to the time t plus omega squared times sine phi is equal to 0. The parameter omega squared is given by the ratio of the magnitude of the gravitational acceleration g to the length L of the suspension string. First, we cast this equation in a more convenient form by introducing a new variable. We will denote the first-order derivative of phi with respect to the time t by the function psi. Then the second-order derivative of phi with respect to the time t can be written as the derivative of psi with respect to the time t. Now we consider psi as a function of the function phi, and we apply the chain rule for the derivative. This gives the product of the derivative of psi with respect to the angle phi and the derivative of phi with respect to the time t, where we can substitute psi into the time derivative. In fact, this expression is equal to 1 over 2 times the derivative of psi squared with respect to the angle phi. Then we can write the equation of motion as a first-order differential equation stating that 1 over 2 times the derivative of psi squared with respect to the angle phi plus omega squared times sine phi is equal to 0. By separating its variables, we can integrate the differential equation, and express the function psi squared as 2 times omega squared times cosine phi, plus a constant of integration written as 2 times c. If we take the square root of both sides of the equation and substitute the definition of psi on the left-hand side, then the equation of motion can be written in the following form. The derivative of the angle phi with respect to the time t is equal to plus or minus the square root of 2 times the sum of omega squared times cosine phi and c. We have still a first-order differential equation, where the sign in the right-hand side of the equation can be determined by solving an initial value problem for the equation of motion. Without loss of generality, we will impose the following initial value condition on the solution to this differential equation. If the initial position of the pendulum is at any of its turning point, then the initial angle phi is equal to the minimum or the maximum angle phi 0, where the speed of the bob vanishes, that is its angular velocity given by the derivative of the angle phi with respect to the time t is equal to t0. Then the left-hand side of the differential equation vanishes if the time t is equal to t0. The right-hand side of the equation only vanishes if the constant of integration c is equal to minus omega squared times the cosine of the initial angle phi 0. Now we can substitute the constant c back into the differential equation, separate its variables and integrate it over an interval measured from the initial time t0 and the initial angle phi 0. As a result, we can write that the time t measured from the initial time is equal to plus or minus 1 over omega, time the integral of 1 over the square root of 2 times the difference between the cosine of the angle phi and the cosine of the initial angle phi 0 with respect to phi from phi 0 to the angle phi measured at the time t. By applying some trigonometric relations, we can write cosine phi as 1 minus 2 times the square of the sine of phi over 2. Similarly, we can write minus cosine phi 0 as minus 1 plus 2 times the square of the sine of phi 0 over 2. Then cosine phi minus cosine phi 0 can be written as 2 times the square of the sine of phi 0 over 2, minus 2 times the square of the sine of phi over 2. If we substitute this result into the integral, then the equation of motion of the pendulum has the following form. The elapsed time t is equal to plus or minus 1 over 2 times omega, times the integral of 1 over the square root of the difference between the square of sine phi 0 over 2 and the square of sine phi over 2 with respect to the angle phi, from the angle phi 0 to the angle phi measured at the time t. If the angle phi 0 is measured at the turning point in the left-hand side to the equilibrium position of the pendulum, then phi 0 is negative and represents the minimum angle of the swing of the pendulum. Therefore, the angle phi increases while phi 0 is always less than phi, and we choose the positive sign in the right-hand side of the equation. If the angle phi 0 belongs to the turning point in the right-hand side, that is phi 0 is the maximum angle of the swing, then the angle phi decreases and phi 0 is always greater than phi. In this case, we choose the negative sign in the right-hand side of the equation. This equation provides an implicit relationship between the elapsed time t and the angle phi determining the instantaneous position of the pendulum at the time t. The parameters of the equation are the minimum or the maximum angle phi 0 at the turning points, and the constant omega depending on the gravitational field at the place of the pendulum and the length of the suspension string of the pendulum. In order to transform the equation of motion into a more convenient form, we will change the variable of the integral in its right-hand side. Let us denote the sine of phi 0 over 2 by the letter k, and introduce the new variable theta with the condition k times sine theta is equal to the sine of phi over 2. In the initial position of the pendulum, where the angle phi is equal to phi 0, k times sine theta is equal to the sine of phi 0 over 2, which is equal to k by definition. Then sine theta must be equal to 1. As a result, in the initial position of the pendulum with the initial angle phi 0, the variable theta is equal to pi over 2. If we compute the differential of the equation used in the definition of theta, then we can state that k times cosine theta, times the differential of theta is equal to 1 over 2 times the cosine of phi over 2, times the differential of phi. Here we can write the cosine of phi over 2 as the square root of 1 minus the square of the sine of phi over 2. If we substitute the definition of theta into the result, then we obtain 1 over 2 times the square root of the difference between 1 and k squared times the square of sine theta, times d theta. We can express the differential of the angle phi from this equation as the ratio of 2 times k times cosine theta to the square root of the difference between 1 and k squared times the square of sine theta, times d theta. We will use this equation to change the variable in the integral of the equation of motion of the pendulum. We saw that this equation states that the elapsed time t is equal to minus 1 over 2 times omega, times the integral of the square root of the difference between the square of sine phi 0 over 2 and the square of sine phi over 2 with respect to the angle phi from the initial angle phi 0 to the angle phi measured at the time t. The minus sign in the right-hand side of the equation indicates that the turning point of the pendulum in the right-hand side was chosen as its initial position, and the angle phi decreases from phi 0 to minus phi 0 in the first half of the period of the motion. If we substitute the parameter k and the variable theta into the integrand, then we can write the time t as 1 over 2 times omega, times the integral of 1 over the square root of the difference between k squared and k squared times the square of sine theta, with respect to the angle phi from phi to phi 0. Here we absorb the negative sign into the integral by exchanging its limits. The integrand can be written as 1 over k times the square root of 1 minus the square of sine theta, which is multiplied by the ratio of 2 times k times cosine theta to the square root of 1 minus k squared times the square of sine theta, due to the change of the variable of integration, and the integration is performed with respect to the variable theta from a given theta to pi over 2. After simplifying the equation, we obtain the final form of the equation of motion stating that the elapsed time t is equal to 1 over omega, times the integral of 1 over the square root of 1 minus k squared times the square of sine theta, with respect to theta from theta measured at the time t to pi over 2. Since the integral in the equation of motion cannot be evaluated analytically, we will only derive an expression for the period of motion of the pendulum in terms of its initial condition and the parameter omega. We chose the turning point of swings as the initial position of the pendulum. Then the bob will cover 1/4 of the path of its periodic motion when it passes through the equilibrium position. Therefore, it takes 1/4 of the period of its motion to reach the equilibrium position from the turning point. As already seen, theta is equal to pi over 2 for the initial angle phi 0. In the equilibrium position, the angle phi is equal to 0, which corresponds to a vanishing theta. Then the period t of the oscillation of the pendulum can be written as 4 over omega times the integral of 1 over the square root of 1 minus k squared times the square of sine theta, with respect to theta from 0 to pi over 2. In fact, we can recognize the integral in the expression obtained for the period of the swings of the pendulum. The integral of 1 over the square root of 1 minus k squared times the square of sine theta with respect to theta from 0 to pi over 2, is known as the complete elliptic integral of the first kind denoted by the capital letter K. Since it is a definite integral, it only depends on the modulus k defined over the interval between 0 and 1. Then the period t of the motion of the mathematical pendulum is equal to 4 over omega times the complete elliptic integral of the first kind, where omega is defined by the square root of the magnitude of the gravitational acceleration g over the length L of the suspension string of the pendulum, and the modulus k is defined by the sine of the angle phi 0 describing the initial position of the pendulum over 2. If the pendulum with a suspension string of a fixed length is installed in a given place with a given gravitational acceleration, then the parameter omega is a constant and the only free parameter is the modulus k, that is the initial angle phi 0. This parameter will determine the period t for a given omega. Here we can see the complete elliptic integral of the first kind as a function of the parameter k. The graph shows that the integral is equal to pi over 2 if k vanishes, and diverges if k tends to 1. The table also demonstrates that the change in the value of the integral is more sensitive in the range close to 1, that is when the initial angle phi 0 is close to the straight angle. Although the elliptic integral of the first kind cannot be expressed in terms of elementary functions, it can be presented as an infinite series. The infinite series of this integral is the sum from n equals 1 to infinity of the square of a fraction times k raised to 2 times n, where the fraction is given by the factorial of 2 times n, divided by 2 raised to 2 times n, times the square of n factorial. This expansion allows us to approximate the period of the motion of the mathematical pendulum with an arbitrary precision. If this infinite series is substituted into the original equation, then the period t can be expressed as 2 pi over the parameter omega times a polynomial of the modulus k with infinite number of terms. We have seen that the pendulum performs simple harmonic motion for small swings with the angular frequency omega. In this case the modulus k tends to 0, and the period t of the motion is reduces to the 0th order of the infinite sum, which gives 2 times pi divided by the angular frequency omega. By denoting the period of the oscillation of the pendulum for small swings by t0, we can see that the period t of arbitrary swings is always greater than the period t0 of the small oscillations of the pendulum, and t approaches t0 as the modulus k, or the initial angle phi 0 tends to 0. This is illustrated in the following table where we show the ratio of the period t to the period t0 for different values of the initial angle phi 0. For a vanishing initial angle, t and t0 are equal, and the deviation of the period t from the period t0 increases with the increasing angle phi 0. The ratio of the periods can only be measured in par per thousand, if phi 0 is equal to 10 degrees. However, its value raises to 1 7/100 for 60 degrees. If the initial angle of the pendulum is set to 120 degrees, the deviation is 10 times greater than the value obtained for 60 degrees. Although the initial angle phi 0 is normally much smaller than 120 degrees, even smaller deviations in the period can be accumulated during several swings. Such a deviation will result in inconsiderable error in time measurements performed with mathematical or simple pendulums. Therefore, it is always important to apply the formula with infinite expansion of the elliptic integral to determine the period t of the motion of the pendulum with the sufficient accuracy.